and welcome to Week 5, Lecture 1 of CO 442642 Graph Theory. Today, we'll be talking about discharging. So what is discharging? Well, it's a counting method, a proof technique used often in coloring, wherein we do the following things. We assign charges to objects. So this goes beyond graph theory, but let's just focus on graphs. So here think of vertices, edges, faces if it's an embedded graph or planar graph, such that the sum of the charges is, say, negative. Could be a specific number, we'll see examples later, but it's best to think it's negative, so below some threshold, namely 0. Or if you'd rather flip everything, all the signs, you could think positive. But let's say negative. So we assign charges to objects such that the sum of the charges is negative, and then we redistribute the charge according to a set of, quote, discharging rules, such that the sum is unchanged. So we know what the sum is, some negative number, and then we have maybe local or perhaps even global rules which will redistribute the charge, but importantly, conserve the total amount. So the sum is unchanged. And then what we do is we derive a contradiction by showing that the sum of the new charges is non-negative, or respectively non-positive if everything was flipped, given the assumed properties of whatever we're trying to prove. So somehow, by this assignment of charges, we know that the sum is negative, but if we move them around, all of a sudden we see that given the properties, the sum has become somehow non-negative, and thus we derive a contradiction. So it's quite a useful technique, quite magical in its way, that if maybe just by picking the right set of rules that then goes with the assumed properties, the configurations we know don't exist, then we can derive a contradiction. So at its heart, it's just a counting method, and it's a bit of an art form. What are the rules that we're supposed to make, and what charges should we assign, but this is the idea. So today we'll go through some of the standard setups for the charges and a number of examples to show you what things can be proved and what rules maybe make sense to choose, and how these proofs go, to give a flavor. So again, the discharging method was key to the proof of the four-color theorem, where the number of rules was quite long. So even in the latest proof, it was 50 plus rules, and so the proof that you get this contradiction actually takes 50 plus pages. So it can be used to prove very hard things, but sometimes they'll be easy ones. So let's maybe start with what do we use as charges? Well, since last time we were talking about coloring or list coloring planar graphs, so let's talk about planar graphs. For plane graphs, so here again I'm going to think of them as plane graphs, meaning they're already embedded. So they have an embedding. Natural choices come from Euler's formula. So if you don't remember Euler's formula, here it is. If G is a plane graph, then V minus E plus F is equal to 1 plus the number of components. So I'm going to write squiggly F for the set of faces of G and squiggly C for the set of components of G. And so if you're connected, of course, this is the famous, V minus C plus F equal to 2, which you've probably seen, but that only holds for connected graphs. So that's Euler's formula. So it's an intrinsic property and an inequality that all plane graphs satisfy. What can we do with that? Well, we can use it as a basis for assigning charge, because we know that somehow the sum on the left is always equal to the sum on the right. So in particular, which is an invariant of the graph. So maybe 2, think if it's connected. So let me show you a common discharging setup for planar graphs, and then I'll show you some more. But let G be a plane graph, and here's an initial charges. So here's things that make sense. Is you choose, I'll denote the initial charges with this CH meaning charge, but 0 meaning initial. So we'll have the initial charge of a vertex will be just its degree minus 6. And then we're going to also charge of the faces to be 2 times F minus 3, where F is the size or equivalently length of the face, which would be, of course, the degree in the dual graph, essentially. Now, what does this buy you? So here I'm not going to charge edges at all, just the vertices, just the faces. These are the only charges. And I claim that actually they sum to a nice number because of Euler's formula. So let's maybe work through this. So if you want to pause and anticipate what the sum of all these charges should be, it has a nice formula. If not, I'll do the calculation for you. So what is the sum? Well, let's just put in the numbers. So charge 0v is degree of v minus 6, and charge 0f is 2f minus 3. And so we're summing over all vertices and all faces. So we can expand that. So we can move the minus 6 out. So it would be minus 6 v of g, and the 2 times minus 3, that'd be minus 6 f of g. And then we have some degree of v and 2 times the sum of the f's, the lengths of the f's. So what is that? Well, now maybe you recall from undergraduate graph theory that, well, the sum of the degrees is 2e of g by the handshaking lemma, and similarly the sum of the f's is 2e of g by the face shaking lemma, or the dual of the handshaking lemma. So you get this, and you can nicely rewrite it, so we can group the e's together and get a 6e, but we also had a minus 6v and a minus 6f, so you write all of that together, and then you can apply Euler's formula, and we know then that's the negative of 1 plus c, so we get negative 6, 1 plus c. So we get a negative sum of charges, and in particular, say if you're connected, you get minus 12 as this invariant. So somehow this is a very nice sum of charges, which somehow takes into account the degrees of the vertices and lengths of the faces, but we know that in total, because of Euler's formula, the properties of embedding, the sum is always negative. It's always negative 12 for connected graphs, and even smaller actually for disconnected graphs. So that's one common setup. So let me just encode that in short form. So this is normally known as like vertex discharging, or I'll call it the vertex centric setup for discharging for planar graphs. So charge being degree minus 6 for vertices, 2 times f minus 3 for faces. The sum's negative 12 if connected and only smaller if not. What is this good for? Well, this is usually good for kind of unrestricted planar graphs, where you're not making any assumptions about the faces of the planar graphs. And why is it vertex centric? So maybe stop and think about that. Well, it's somehow we already know that the charge of the faces is non-negative. So if you want to derive a contradiction, somehow maybe your rules only deal with vertices or more with vertices, and it's trying to make the negative vertices, which if you think about it are the ones of degree at most 5, positive somehow. And then that would be enough, if you didn't mess too much with the faces, to derive a contradiction. Yeah, there are other setups. I mean, there are really infinitely many setups. Another common one used is a face-centric setup, or also called face discharging, which is just the dual or symmetric form of the vertex one above. So there we have the charge of a vertex b2, degree of v minus 3, charge of a face b, start at f minus 6, and then for the same reasons the sum would be minus 12 if connected and only smaller if disconnected. And what is that good for? Well, cubic plane graphs are nice, because then the charge of the vertices would be 0, and then it's only a question maybe of the faces, and maybe trying to make the negative faces, i.e. the faces of size at most 5, positive to derive a contradiction. So there's vertex-centric, there's face-centric. Well, you could do a balanced approach. So here's a balanced setup where somehow vertices and faces are kind of weighted equally. So we make the charge of a vertex be degree of v minus 4, the charge of a face be f minus 4, and the sum be negative 8. So it works out slightly differently because you get 4 e minus v minus f, which then would be negative 8 if you're connected, and again only smaller if disconnected. What's that good for? Well, so here we're kind of balancing the charges, so this might be good for triangle-free plane graphs, because then you might have that the faces are actually positive in this setup. We're getting more out of the kind of lowering the charges, or rather upping the charges of the vertices. Could be good for restrictions on triangles. So somehow if you don't have too many small degree vertices or faces, this might be a good setup. And I won't go through it, but of course, really you could pick, using Euler's formula, you could pick essentially any convex somewhat combination you want. So if you balance the degrees minus something and the faces minus something, so that you can end up with Euler's formula. So there would be a whole plethora, a whole spectrum of possible weightings, even beyond the vertex and face versions, but certainly for anything in between, so as to how to balance the appropriate charges. So I won't state that more generally, but these are the 3 somehow most useful, most common setups. All right, so that's what I wanted to say about the discharging setups. And now I'm going to turn to doing examples. So here's I'll do 3 examples today, and then that will conclude our discharging, and we'll move on to surfaces for the rest of the week. But here's a first example, some notation. So just to make all of the writing simpler when I talk about rules, when I go try to do little proofs and the statements, this is very common, people have done this for discharging, adopted this following system. So a k vertex is a vertex that's degree is k. Well, a k plus vertex will be degree is at least k minus vertex will be degree of most k, and similarly for faces, we'll talk about a k face, a k plus face, and a k minus face. So then here's our first example. Here's a proposition we'd like to prove with discharging. Every plane graph with minimum, that's little delta of g, that's the minimum degree of g is at least 5, contains a 5 vertex that's adjacent to a 7 minus vertex, so a vertex of degree at most 7. So you know by Euler's formula that of course it would contain a 5 vertex, but actually you can show the stronger property that you can find a 5 vertex that's next to some relatively small vertices. And you can prove other variants of this, finding what just kind of happens in general plane graphs, but let's prove this one using discharging. So what is the proof? So we have to pick a set of charges, right? We have to pick a setup. Well, I'm going to use the vertex-centric setup because we're mostly concerned about vertices. There's no restrictions on the faces. So we'll have charge 0 of v be degree of v minus 6 and charge 0 of f be 2f minus 3. And then again, the sum is at most negative 12. So here I'm not assuming connected, but certainly it's at most that. So then you have to think through what's going on. So the faces already have positive charge, or non-negative at least. The vertices, well, only the 5 vertices will be the problem because we have minimum degree 5. They're the only ones with negative charge. So if we could somehow redistribute their charge while keeping everything else non-negative, then we'll get a contradiction. So here's the rule we come up with. We say that every 8 plus vertex sends a quarter charge to each neighbor. So I could flip this around. You'll see, and think about it as the 5 vertices sending some of their negative charge, but here I write it in a positive way, that every 8 plus vertex will send a quarter charge to each neighbor. And what do we know? Well, the 5 vertices are adjacent to smaller things, so they'll be adjacent to a lot of 8 pluses, so they'll receive a lot of charge, and we just have to argue that everything's non-negative. So let CH without a 0 denote the final charge after applying this rule. So we just apply the rule everywhere. We get a new set of charges that'll be denoted by CH. And then our claim is that all these final charges are non-negative. And once we've done that, we'll have derived a contradiction, because clearly the rule doesn't change the sum, right? We're just moving some charge around, redistributing it from one vertex to some of its to neighbors. So that will provide the contradiction. So we go through all the cases now. So here I'll bold them. So faces. Well, the faces had initial charge of 2f minus 3, so they're always at least non-negative, and they also don't move around their charge, so they'll just be fine. What about 8 plus vertices? Well, they're the ones giving away a lot of charge. So the charge of them is, well, it's degree of v minus 6, that's the initial charge, and they could give away a quarter to every neighbor. So that's a degree of v over 4. So if you rewrite that, you'd get 3 degree of v minus 24 over 4, but since the degree is at least 8, that number is always non-negative. So 8 plus vertices will be fine. 6 and 7s, well, they aren't involved in the charge rules, so they will end up with, technically, sorry, they could end up with more charge than they started with, because they could have 8 plus neighbors, but they'll end up at least as good. So they'll be fine. And then the 5 vertex, well, the charge there would be, it's negative 1, and it gets a quarter from every neighbor, because every neighbor of it is an 8 plus vertex, and so it'd send a quarter to v by our rule. So we get minus 1 plus 5 quarters, which is a quarter, which is, of course, greater than 0. So all of the vertices will end up non-negative, and the faces are non-negative, so the sum is all non-negative, and that's a contradiction. So of course I should write that out if I was doing a formal proof, but here we're just going through the ideas. So that concludes our first example. So there we mostly just dealt with the vertices and used the vertex-centric setup and didn't worry too much about the faces. Here I'll use a different setup, so I'll do a second example where every plane graph with minimum degree 3 contains a 3 vertex incident with a 5 minus vertex face, or a 5 minus vertex is incident with a 3 face. So either you can find a 3 vertex incident with a triangle, 4 cycle or 5 cycle, or a 3, 4, 5 vertex that's incident with a triangle. So that's what we need to show. And here I wrote it like this so to show you the symmetry. So what setup should we use? What set of charges? Well, you might see that the statement is very symmetric between vertices and faces, so a balanced setup should be a good approach. So we'll do charge 0 of v being degree of v minus 4. The same for faces, it's f minus 4, and the sum's at most negative 8. And then what do we know? Well, we're going to do rules. So one rule we'll do is every 6 plus face sends a third charge to each incident vertex. So the only issue in the balance setup is the triangles and 3 vertices have -1 charge. Everything else is non-negative. So if we could give them charge, it would be good. Where should we get that? Well, we know 3 vertices are only incident with 6 plus faces, otherwise we'd be done. And so we'll have the 6 plus faces. They have some extra charge, at least 2, so they'll send a third to each incident vertex. And then this will help prepare the 3 vertices. We could just make this the 3 vertices, but we'll say to each incident one. And 6 plus, then we'll do the symmetric rule that every 6 plus vertex will send a third charge to each incident face. Because again, the 3 faces, which are negative, are incident with only at least 6 plus vertices, so they can get some charge from them. So these are our 2 rules, highly symmetric, and now we just have to proceed showing that after these rules, where we have a final charge, again we'll denote with CH without the 0, that the claim is that all the final charges are non-negative, and then we'll get a contradiction. So how do we do this? Well, we look at the 6 plus vertices. They have charge degree minus 4, and they send at most 1/3 to every incident face, which is degree of v if you think about it. So that would get you 2 degree of v minus 12 over 3, which is at least 0 because the degree of v is at least 6. 4 vertices and 5 vertices will essentially remain unchanged, so they could end up picking up some vertices off the some extra charge actually off the faces, but we could have ignored that, so we could have actually just said they're equal. And then we know they're non-negative, so they don't give away a charge, so they're good. And then what about the 3 vertex? The problematic ones, they have charge -1, but they pick up a third from every incident face, since every incident face is a 6 plus face by the assumption, and so then it gets a third by rule 1, so -1 plus 3 times a third is 0, and so they're also 0. So that covers the vertices. Then we have to check all the faces, but as you probably see, this is just symmetric for faces, so we're done. So it's nice we use the balance setup because the problem was highly symmetric, and then really we just have to do vertices because we made the rules symmetric and the faces are just the same. So that was our second example. So we've seen a vertex-centric setup. We've seen one where it's kind of balanced. So for our final example, I'll do a crazier one. So here's a proposition. Every plane graph with minimum degree 3 contains one of the following. So here are 3 options. You get 2 adjacent 3 faces, or a j face for some j between 4 and 9, or a 10 face that's incident with only 3 vertices. So this is kind of very nice. Either you get kind of 2 adjacent triangles, or you get some small face between 4 and 9, or a 10 face incident with only 3 vertices. In particular, there's something between kind of 4 and 10, or 2 adjacent 3 faces. Why is that good? This should remind you of something from last class when we talked about coloring plane graphs, namely Steinberg's conjecture. And so actually a corollary of this is that every planar graph with no 4 to 9 cycles is 3 colorable. So remember that question of Erdos, what's the minimum k where no 4 to k cycles is 3 colorable? Well, the best known is 7, but here's a nice corollary that you get 4 to 9. So here's a short proof that 4 to 9 works. So let's maybe go through that. So here's just a sketch. But what would you do? So you could stop and think, but really standard reductions would show that G is 2 connected. And we may assume, and then that it has minimum degree at least 3, right? So if you weren't connected, you'd do this over components, and if you're cut vertices, you could glue the colorings. So you're going to assume you're 2 connected, and the minimum degree at least 3. Why is that? So maybe think about it. Well, otherwise you delete the vertex, get a coloring by adduction, and extend back because they'd only have 2 neighbors, so there'd be a color for that one. So that's the standard stuff. Then what? Well, what do we do next? So maybe think again, maybe pause. What would be the next step? Well, it's corollary, so we're going to use the proposition. So what do we get from the proposition? Well, the first case doesn't happen, because two adjacent three faces would be a 4 cycle. The second case doesn't happen, because those are 4 to 9 cycles. So you only get the third case, that there's a 10-face incident with only 3. So actually, we'd already have shown, if it was no 4 to 10, that we'd be done. But now we have to deal with these 10 faces. What do you do? Well, this one, slightly less obvious, but you delete the cycle, all the vertices, you color by induction, and it turns out you can always extend. So this is a well-known fact in list coloring that even cycles are 2 list colorable, right? So they had 3 colors, they'll have one neighbor outside because they're degree 3, and so then because they don't have then there's no chord of the cycle because there's no 4 to 9 cycles, and so then what you get is that you'll end up with a list of size 2. So each vertex will have 2 options of 1, 2, 3, and that always has a coloring. So then it will extend, and we're done. So that was a nice short proof assuming the proposition. So just giving you a taste here that Steinberg's, so here's kind of a very baby version of it that will do with discharging. But actually that 4 to 7 proof as well uses discharging to find kind of reducible configurations, and then does this reduction minimality pre-colored cycle tricks. So just a bit more involved for our purposes. So instead we'll just do this simpler version. So okay, how do we prove this proposition, right? So we've done our corollary. How do we prove the proposition? Well, we need an assignment of charges, a setup. What setup should we use? Do we want to do vertices? Sure, we could. Balance maybe makes sense because it's somehow about triangles. Or maybe we could do face. And honestly, that's, there's somehow always a more natural choice perhaps, but no choice is really wrong because worst case, you can get between the different setups with just adding some extra rules that essentially would shift the charges to what they should have been. So the question is more, which is the setup that gives you the smoothest route to a proof. And so I'll just tell you for this, one natural one that works is face-centric. So you have the charge of the vertices be 2 degree of v minus 3. Charge of the faces be f minus 6. Again, the sum will be at most minus 12. It'll be negative. So here's our face-centric setup. What should be our rules? So this one's hard, so I'll go ahead and show you the rules. So our first rule has to deal with 3 faces, right? So what are the things with negative charge? Well, the vertices are fine because it's face-centric. It's only 3, 4, and 5 faces. We don't have 4 and 5 faces, so it's only 3 faces. So we need to give them some charge. And they have negative 3, so they need a lot. So here, rule 1 kind of cures the triangles. It says that every 10 plus face sends +1 to each adjacent 3 face. So that'll cure the triangles because you don't have triangles next to triangles. So then you'll end up getting 3 from all the neighbors, and we'll go through that, but they'll be fine. So that's first step. We have to cure that. But then the problem is the 10 plus faces may be next to 10 plus triangles, so they could lose too much charge. So we need a rule to cure them. So then we invoke the next rule, which is rule 2. We say that every 4 plus vertex v sends +1 to each incident 10 plus face f, where v is contained in a triangle sharing an edge with f. So here's the picture. So we have this 10 face f, 10 plus face f. Here's v, it has degree at least 4, and we know that it's in a triangle that's adjacent to f, as depicted. So then we'll send a charge. Why do we do it like this? Well, you'll see it's what works out, but essentially, we obviously can't look to 3 vertices because they just don't have any charge, but 4 pluses have some charge. And where should they give it? Well, they don't need to give it to the triangles because of rule 1, so then they should give it to 10 plus faces. Which ones? Well, it just kind of turns out it's 10 plus faces next to triangles that are the ones in peril, so this is a nice rule that kind of makes sure that only the ones that really need it get the charge. Because if you just try to distribute equally among 10 plus faces you're incident with, turns out the numbers won't quite work out there. So then these are our 2 rules. So maybe again stop and pause and try to digest these rules. And here I've drawn some nice pictures for you. But now let's go through, these are the rules. So again, we enact them all at the same time, applying them all together. And then the question is, what's the final charges? So let CH again denote the final charge after applying both rules as much as you can. And then the claim is all final charges are non-negative. So that's always our setup, right? We have the sum is, you say, negative, and then we do rules, and we'll show it non-negative. Or if you need to, you can be more specific. If it's, the sum is at most minus 12, so long as we know the sum is at least, say, minus 11, then you'd get a contradiction. But here it works nicely, just doing negative to non-negative. Okay, so let's think through this. So we have to check everything. So we have to check vertices and faces. So let's start with vertices. Well, the three vertices just don't have any charge, and they don't really move charge, right? So we had two rules. Rule 1 goes between faces. Rule 2 gives from higher degree for 4 plus vertices. So 3 vertices will be fine. So that's not, and we built the rules to do that, right? The 4 plus vertices, we have to check that they don't lose too much. They start with 2 degree of v minus 3, and then they give away, this number of 1 to every incident 10 plus face where they share a triangle, which is weird. But it turns out if you count that number, then turns out the number of faces it can give to is at most 2 degree of v over 3 floor. And then if you do out the math, then you get 4 degree v over 3 ceiling minus 6, which is non-negative since the degree of v is at least 4. And so why is that? So let me just say a little bit. Well, think about it. If you're this vertex, well, you kind of always, every face you need a triangle next to it, and you're not sending to triangles. So somehow the worst case is kind of large face, triangle, large face, and that they come in threes, kind of large face, triangle, large face. And so then you need, if we're going to, turns out you can give at most to 2/3 of your neighboring faces. So that's the 4 plus vertices, it just perfectly works out. What about the faces? So the 3 faces, remember we built rule 1 to pay them. So they started with minus 3 charge, and they receive 1 from every incident adjacent face. Since every adjacent face is a 10 plus face, since we don't have adjacent 3 faces and we don't have smaller 4 to 9 faces, so they will get plus 1 from those. So they'll get plus 1 3 different times, so they end up at 0. Okay, so that's great. And then the last part to check is the 10 plus faces. Why are they not negative? Well, that's really hard. I mean, you could go off and think about it on your own some, but it's maybe not so immediate to see because, okay, they could give to a lot of triangles, but maybe they're kind of made up for by these high degree vertices paying them. Turns out, actually, they really are. So there's a nice way to think about it. It goes like this. You think in terms of paths along the boundary of the face. So you think of a path, a maximal kind of path, where the neighboring faces are triangle and the ends are degree 3. So you think about, your triangles as coming in kind of paths. You have triangles, then you have a non-triangle, triangles, non-triangle, it splits up. So in such a path of triangles, what happens? Well, you lose 1 to each triangle on the path by rule 1. You have to pay your neighboring triangles a 1. But you gain. So this is the key insight. You gain. If you look at that picture, right, if you have 2 triangles in a row, the vertex in the middle has to be a 4 plus vertex. Do you see why? Because you don't have adjacent triangles, right? Adjacent 3 faces. So that means you actually has 4 different neighbors, and so it's a 4 plus vertex. And so by rule 2, it will pay f back 1. So somehow, when you look at these paths, I pay 1 out to the triangle and get paid back. 1 out to the triangle, get paid back. So what happens in total is you get a net loss of 1. And that's only because if the ends are degree 3. If actually the ends were degree 4 or higher, either one, then one of the ends would pay us 1, and we would actually end up with a net loss of 0. So the only, somehow if we kind of group the triangles with also their internal and or end vertices that are paying us, then they mostly balance out. So we just have to wonder how many faces, how many of these paths do we have to pay? Well, the net loss is then at most the number of such paths, which is at most f over 2, rounded down, right? Each path of triangles, these are disjoint, and they use at least 2 vertices, so really at most half of the things can be these paths. Now there's also the case where the whole thing is just a cycle, but then you actually have triangles, but then you don't lose anything, and that's fine as well. So our net loss is at most f over 2, rounded down. So now we just go through. So if you're an 11 plus face, our charge was f minus 6, and we lose f over 2 rounded down. That makes f over 2 rounded up minus 6, which is at least 0 if f is at least 11, right? You get 5.5, which would be 6 rounded up. That'd be good. So that would show that 11 plus faces are fine. So if we weren't worried about 10s, we'd just be done if we just said there's no 10s. But we have to show this 10 face. Well, the 10 face, it turns out, you go through that argument, they would have charge initially of 4, right? F minus 6, 10 minus 6, that'd be 4. And so if they only lost 4, if they only had 4 of these kind of bad paths, then we'd be fine, we'd have 0. So they have to have 5 such bad paths, which are triangles with the ends being degree 3. But think about what that means. I mean, they're disjoint, so I only have 10 vertices, so each such path is just a triangle by itself. And the ends of that path are degree 3. So that means all of the vertices incident with my 10 face are actually degree 3. And so then that is a contradiction, because we get a 10 face where it's incident to only 3 vertices, contradiction. And so then that concludes our proof of the proposition. So 11 plus face was easy, 10 face a little bit harder, but we're nice to think of the path. So this was our final example. It's a nice one because it has implications with the coloring, as with Steinberg's, and it had some more non-trivial rules where we went between faces and we paid back from these higher vertices, but only to faces that kind of needed it. And we built it in such a way that kind of there were easy things to check that was nice. You know, we made the first rule to handle triangles and such, but then we added the second rule to pay back our large faces, and it turns out it works out. Everything works out just perfectly, and is tight, and we just end up with a proof there. So we get a contradiction. If we assumed, you know, no adjacent 3 faces, no 4 to 9 faces, and no 10 incident to only 3s, we'd get a contradiction because the sum again would be non-negative, and we started with negative, and we didn't change the sum, so contradiction. So that's discharging in a nutshell, that if you can move the charge around and then find out by kind of local rules that you get a contradiction, that everything somehow is non-negative. So it's very mysterious and magical and kind of an art form, what rules to pick, but maybe you got some flavor of that. We look to things that are non-negative, and we kind of ask how can we have them send the charge in such a way that we'll end up with somehow these non-negative charges, assuming that we don't have whatever local structures we're dealing with. All right, so that concludes the lecture for today about discharging. For the rest of the week, we'll be talking about surfaces and starting on that. So until next time, see you then.